Look around almost any modern city, and steel is absolutely everywhere. And the crazy thing is, you often can't see a single trace of it. It's buried deep underground, it's wrapped up in concrete, and it's hidden right behind the sleek glass facades of our buildings. We honestly take it entirely for granted, yet it is quite literally the invisible foundation of the modern world.
So, you might be wondering, what really holds the modern world together? Well, the answer to that question starts with something remarkably simple. It all begins with iron, just a basic chemical element combined with a relatively tiny amount of carbon. And as we're going to see throughout this explainer, that incredibly small addition of carbon changes absolutely everything.
Section 1. The hidden foundation.
Steel holds up our skyscrapers and reinforces the concrete we drive on every single day. It forms our railway tracks, our bridges, ships, cars, and pipelines. But you know what's really fascinating? It's that last point. Steel literally forms the machines that make other machines. We're talking machine tools, massive mining equipment, industrial presses, molds, turbines. The entire infrastructure behind global manufacturing itself depends heavily on steel. We are just constantly surrounded by it.
Section 2. From ore to iron.
To understand steel, we have to look back a bit. Iron is actually super abundant in the Earth's crust, but usable metallic iron, that's rarely found just sitting on the surface. It's chemically bound to oxygen inside minerals. Now, by the 2nd millennium BCE, early communities were using furnaces to heat iron ore together with charcoal. The charcoal provided the intense heat, sure, but its carbon also pulled oxygen away from the iron. Now, these early smiths didn't get molten iron. Instead, they got this hot, porous mass called a bloom. They would repeatedly heat and hammer this bloom to literally squeeze out the impurities. But here is the absolutely crucial cause and effect. By doing this over and over, carbon from the charcoal was unknowingly being forced right into the iron. They were making early steel and didn't even know the chemistry. Fast forward to the 1850s, and Henry Bessemer patents the process that blows air through molten iron. By using oxygen to rapidly burn off impurities, this innovation finally allowed us to produce this material on a massive industrial scale, fundamentally shifting the entire course of human manufacturing.
Okay, let's dive into this and look a little closer. Section 3. The atomic secret.
So, metals are made from atoms arranged in repeating crystal structures. But these structures are actually far from perfect. They contain defects, specifically line defects called dislocations. When a metal permanently bends, these dislocations are basically moving through the crystal. Think of an iron crystal like a highly organized, dense crowd of people trying to shift past itself. When you add small carbon atoms to the mix, they occupy the tiny empty spaces within that structural lattice. They act like highly effective physical obstacles, making it so much more difficult for that organized crowd to move and slide past one another.
Pure iron, just on its own, is relatively soft and ductile. But when you introduce carbon in highly controlled amounts to create carbon steel, you are physically blocking those dislocations. And making it harder for dislocations to move microscopically means a massive increase in strength and resistance to deformation macroscopically. So a relatively small chemical change down at the atomic level produces a major mechanical change in the real world.
But wait, carbon does a lot more than just block movement. Depending on the temperature and exactly how the metal is cooled, the iron-carbon system forms entirely different microstructures. You can get iron carbide, which is known as cementite, or a layered structure called pearlite. Crucially, when certain steels are heated up and then cooled very rapidly, a process we call quenching, they form martensite, which is incredibly hard. This sudden, drastic temperature drop essentially locks the carbon atoms in place so fast that the crystal structure becomes highly stressed and distorted. What does this mean for us? It means two pieces of steel with the exact same chemical composition can behave completely differently just based on their heat treatment history. One piece might be soft enough to comfortably stamp into a car door, while the other is hardened enough to serve as a high-speed cutting tool. It's like a superpower.
Section 4. Scaling up steel.
So how do we actually make this stuff today? Here is the modern journey. Step 1. Iron ore is introduced into a massive blast furnace, along with limestone and coke, which is a highly concentrated fuel derived from coal. Extreme heat reduces the iron oxides into a steady flow of liquid iron. But there's a catch. This liquid has way too much carbon. So, step 2 is the basic oxygen furnace. Here, pure oxygen is violently blown right into the molten iron to forcefully burn off that excess carbon and any other unwanted elements. Then, step 3. Specific alloying elements are precisely added to create the exact chemistry needed for whatever the final application is going to be. Finally, step 4. The molten steel is continuously cast into massive intermediate shapes, like slabs or billets, ready to be rolled or forged into workable everyday products.
But there is actually another immensely important route, which I really like to call the infinite loop. Steel has this enormous industrial advantage. It can be recycled repeatedly without losing any of its core properties. Today, electric arc furnaces use incredibly powerful electrical arcs to melt down scrap steel. This literally means the steel in an old, broken washing machine can be melted right down and reborn as a structural beam for a brand new skyscraper, over and over and over again.
Section 5. Trade-offs and weaknesses.
Now, engineering is always about trade-offs, right? And one crucial trade-off here is weight. Most steels have a density of about 7.8 grams per cubic centimeter, while aluminum is roughly 1/3 of that. So you might reasonably ask, why don't we just replace steel with aluminum everywhere to save weight? Well, it fundamentally comes down to cost and performance. Steel is generally inexpensive, especially for the incredibly high mechanical strength that it provides. Plus, the global manufacturing infrastructure to make it already exists everywhere. It is simply too strong, too adaptable, and way too cost-effective to replace in the vast majority of heavy-duty applications. But then we have to talk about steel's greatest enemy, rust. Ordinary carbon steel, when exposed to water and oxygen, will rapidly corrode. And unlike some other metals out there that form a nice, thin, durable protective layer when they oxidize, iron rust is porous and it flakes away. So the corrosion just keeps eating deeper and deeper into the structural material until it fails. Material scientists are fighting this battle constantly. They use paint, they galvanize the steel by coating it in a sacrificial layer of zinc, they use electrical cathodic protection for things like massive underground pipelines, or they alter the chemistry entirely, like by adding chromium to create stainless steel.
Another really significant challenge is the environmental impact. Traditional iron production using blast furnaces and coke requires enormous amounts of energy and releases substantial carbon dioxide. Because humanity produces steel on such a massive, completely unprecedented scale, this is a major engineering challenge for the industry right now. Researchers and steelmakers are actively investigating several approaches to address this, including hydrogen-based iron reduction, increasing the use of those electric arc furnaces for recycling, improving overall furnace efficiency, and developing new carbon capture technologies.
Section 6. Building the modern world.
And it all leads to this incredible number. Billions. That's with a B. Global crude steel production is measured in billions of tons every single year. Very few engineered materials have shaped human civilization at a comparable scale.
But remember, there is absolutely no such thing as a single generic steel. Engineers don't sit down and ask, should we use steel? No, they ask, which steel? There are thousands of customized grades out there. Low-carbon steels are highly formable and weldable, perfect for a car body that needs to absorb crash energy safely. High-carbon steels are incredibly hard and strong, perfect for a cutting tool or a gear that needs extreme wear resistance over years of punishing use. Add chromium, and you get stainless steel for a surgical scalpel or your kitchen sink. The profound beauty of this material really lies in its infinite adaptability.
Perhaps the most important concept in materials science is this. Composition changes structure, structure changes properties, and properties determine applications. By tweaking just a fraction of a percent of carbon or carefully controlling exactly how fast the metal cools down, we completely change how the atoms arrange themselves. That invisible, microscopic structure creates the tangible, real-world properties that allow engineers to build everything from razor-sharp tools to the massive skyscrapers piercing our clouds. We learned to control the microscopic world, and in doing so, we built the massive modern world around us. So it leaves you wondering, how many other invisible materials are shaping our daily lives without us even noticing?